Okay, so we're very happy to have Angela Gibney from UPenn. And she will talk about towards more vector bundles or modulated curves from vertex operator out.
Well, thank you for the invitation and happy birthday. My first talk is a postdoc experience. Anyway, it's really great to do that. So I'm going to talk about the topic you might not have really thought about this stuff, which is vertex operator operators. And so I'll say what they are and give some examples and try to indicate how to think about that. They're actually, to get an algebra structure out of them, it takes a little time. So I'm not going to explain what that part of this story is, but I'm going to tell you about algebraic structures on the moduli curves from representations of vertex operator algebras. And so before I get started with the definitions, let me just tell you this is joint work by collaborators Chern and Damiolini, Tarasca, and new work with Krashen. I'm going to talk about some papers. Also, DPT, we have 3 papers on the archive. I sort of summarizing a lot of things from them. A paper with Chern and I, and then new work with tautological. Okay. Which it's almost ready, it's almost on the archive. I'll submit it to the volume if we have a volume for this conference. So I'll talk about sheaves on moduli curves. These are, I'll talk about what moduli curves I'm talking about in a minute, but these depend on a vertex operator algebra and n-tuples. And I'll define those too. Really, this is all about the modules over a point in an unexpected stable curve of genus G. The fibers are the fibers look like quotients of the tensor product of the modules. And they're coinvariants. They're the largest quotients of this tensor product. On which a natural Lie algebra that's determined by the point and a vertex algebra acts trivially. So to get to a place where I can define the Lie algebra, its action, and the vertex, and the modules, it's going to take a little while, so I'm going to do the exact opposite of the last talk, but I'm going to tell you the observations first to motivate why you might, as algebraic geometers, be interested in these VOAs. They're really naturally, modules over VOAs are naturally associated to curves. And there's been some work done by Krashen Lee to generalize these algebras of vertex operators to higher dimensional contexts. So maybe in the future, these could exist in a more general context. So what I'm going to do is use a table to record our observations so far. And I've started to make the table here. I want to put it in three parts. So you won't be surprised.
Could I ask a very stupid question?
Yes.
Are the WI in some kind of correspondence with the mark points?
Yeah, okay, let me say a little bit about that. Right, so to define these, we're going to attach a module over the vertex algebra to each of the marked points. And actually, this is a good time to talk about a little bit about the moduli space of curves. So we work with the stack. So the stack parameterizes families of n-pointed curves of genus G, which are stable according to Delian-Mumford's definition. And so all the results that I'll write down are actually true in families that I want to save time, and I'll write them for points. Of course, the stack is firstly represented by a projective variety, the moduli space of curves, and it really doesn't matter whether you want to think about the object, moduli of curves, as a variety, scheme, or stack. As we all know here, we're interested in the birational geometry of algebraic varieties. The point is to study the maps emitted by the object. And so for that reason, we're interested in, well, sheaves. We get the sections for our maps from the sheaves. And of course, properties of the sheaf can be translated to information about the morphism. We have a globally generated vector bundle, then we have not just a map, an actual morphism. And I'm interested in getting more maps on the modulus that's curves. So I have maybe gone to great lengths to try to obtain more maps. So this is what I want to tell you about today. So the vertex algebra, and I'm going to define it more carefully in a minute, but generally it's a four tuple. The V here is a vector space, and it's we're taking nice VOAs. They're of CFT-type. They're a lot more general examples, and we can even restrict to self-dual and simple, although we don't really technically have to, but it makes some statements easier. But it's an infinitely graded vector space, graded by the natural numbers. The dimension of the components are finite, excuse me. I'll tell you more about this later. One spans the degree 0 component. So it's an element in degree 0. Omega is an element in degree 2. And Y are linear maps that produce ND value power series, which I'll tell you about. It's because the vertex algebra is an infinite object. To study it, it makes sense to find an object that reflects its properties that's finite. And one important way of doing that is to define an associative algebra. It's a quotient to B by a two-sided ideal. And what's nice about this associative algebra is I want to go to the side here and say that there are two functors. So the associative algebra reflects the model structure for B. So there are two functors that I'll refer to. One is, these go from A of B modules. And basically it takes an A of B module to a B module. The construction is a verbal model construction. So really there's a universal enveloping algebra involved. And you can go back precisely to the lowest degree component. And here, this gives correspondence, gives a one-to-one correspondence between simple animals. Simple A and B modules and simple B modules. The story for indecomposable modules is a little more complicated. This functor going from A of B to B modules takes indecomposable modules to indecomposable, but there are more generally indecomposable modules over B. And then there's something that we generalize, which is a bimodule version of this. So it takes A and B bimodules to, there's universal enveloping algebra there. This is important for what I'm going to tell you now. So the fact that A and B reflects the module structure for B lets me, when I make my list of our observations, I can translate that into A and B, and sometimes it's less technical. And so then I can say something about these coinvariants, these sheaves of coinvariants. So this is the list. I'm going to get this over the beginning of the talk. You should see that, right? You can see the columns. Can you still see them? Okay, because the vertex algebra is this infinite object, I said that we want to make it somehow finite. So there are different ways to do this besides taking a quotient. There are different kinds of conditions that have really funny sounding names. There's C1 cofiniteness. which just translates into the algebra A of B being finitely generated. And C2 cofiniteness, there's actually a very infinite list of these. But actually C2 implies all the other ones. And this is the condition that A of B is finite. And in this case, we know that the sheaves are coherent on the interior space of smooth pointed curves of genus sheaf. So if we add a little bit more, adding to the finiteness, if we say that these are rational, and this is not rational like in our world, but if A of B is finite in some symbol, then these are actually coherent and locally free. So they're coherent on all of them in bar. Plus locally free. So these are vector bundles. But these vector bundles really are nice, behave very nicely with respect to the modular space of curves. So I want to get a tutorial with respect to MGN, with respect to boundary constraints. So in fact, these this 1 and 2, if these satisfies 1 and 2, then the sheaves are functorial with respect to tautological. Restriction. So for the grad students, I'm going to draw some pictures. The sheets are really boring and nicely behaved on the interior, but on curves in the boundary, they have some nice properties. So if we take an irreducible, an element of the irreducible component of the boundary, this looks like a curve with the general element looks like a curve with a single node and some marked points. The bullet for the marked points, the moduli and these are the same marked points. And this boundary component receives a surjective map from MG minus 1 and plus 2, where we just have a curve of genus T minus 1 with the marked points P plus and 2 extra marked points. And the map is attached to points. This is a tautological clustering map. And we also have similar clustering maps on the other boundary components. So MG1 and MG2 and 2 plus 1 projected onto the other boundary components, which we can label G1. And I'll call these like here, here, 1, 2, and plus and minus, and these are just attached. So algebraic structures on the modular space of curves that, like for example, homology classes that are closed under whole maps of such tautological maps, also point dropping maps. These are easier to study. And for example, such homology classes live in the tautological ring. And one of the important results about these sheaves is that they behave well with respect to such restriction. So if I look at a fiber of the sheaf at a pointed curve with a node, then it turns out that it it's isomorphic to an analogous object on the normalization, for example. And the way that you get the analogous object on the normalization is that you tensor with the v squared module associated to this A of v. So I think I've erased it now. There's a, so I'll just remind you really quick. There are compatible functors that take A of v modules, and A of v bimodules. A of v is bimodule over itself, in fact, to v squared modules. And apply this functor, sending, for example, the A of v bimodule itself to the v squared module, and so it has two actions, a left action and a right action, and make the coinvariants on this normalized curve with the same mark points but these extra mark points, p plus and minus. You get the you get an isomorphic vector space. So in our original paper, DBT2, we proved that this is true, this isomorphism is true if V is C2 cofinite, so C2 and rational. And in newer work with Chern and Damiolini, we actually were able to drop this rationality assumption. So we always get this isomorphism. And now what that means is that you can translate information about the module structure for A of V over to the module structure using these functors. So for example, if A of V is finite and semi-simple, then it has a bimodule decomposition. It factors as a sum of left and right modules, namely the simple module and the dual. This is a finite sum over simple A of V modules. So, these are all, the whole, there are only finite limiters and finite algebras, and simple is what it means. We call this a bimodule decomposition or bimodule factorization. And so you can transfer that bimodule factorization and apply use functor to those components and get V modules. And then there's a splitting that happens where this is the fibers now look like a sum over simple V modules because of the one-to-one correspondence. So these are fibers of the normal. Okay, so what this says is that these sheaves really behave nicely on the boundary. They break up into finite sums of analogous objects on the normalization of the curve, where the extra marked points are assigned all possible simple modules and their duals. And so, in fact, this allows you to prove that sheaves are coherent on MPN and that they're locally free. And in fact, assuming these extra conditions that that V is assuming the extra condition that V is simple and self-dual, their Chern classes, which we have formulas for, are in the tautological. So I'm continuing this on. So if in addition V is simple and self-dual, then the Chern classes are tautological. Okay, so you can compute the Chern classes, and then you can think about which ones are not. And or you can start with the bundles and ask which of these bundles are globally generated. And so Chern and I started to think about this problem, and what we found is there's a lot of variation. The most general result we have is that if V is generated in degree 1, then the bundles are globally generated if the genus is 0. But we saw a lot of other examples of globally generated bundles. And then we were able to show that some were not globally generated by computing their Chern classes and seeing that they're not net. And it's interesting that in genus 0, you get way more net things, net classes. Part of the problem is that there's something attached to a vertex algebra at central charge, and if the central charge is negative, then it rules out that central charge will rule out the Chern classes being positive. So this class of VOAs, the rational class, has all non-negative central charge. So the rational and C2 cofinite VOAs have the potential of being a source of new Neff classes on the modular space of curves. We know we get new Neff classes, but perhaps giving us enough new Neff classes to show that certain conjectures about the cone being polyhedral may be wrong. So that's the goal, that's the hope, that maybe we have a lot more Neff classes. And so, but I said that we were able, in this recent work, to drop this condition that V is rational. And the reason that we have looked into that at all is that whenever I give a talk about the subject to VOA people, they all want to know if these results hold for non-rational VOAs, because they have motivation from modular tensor categories that this condition actually that you need for locally free, or that is useful to show the sheaf is locally free, they believe for other reasons that you should still get that result even when the vertex algebra is not rational. So that brings us to the less restrictive condition and our good work. So the less restrictive finiteness condition is that the sheaf is finitely generated. There are lots of examples of this. And so what we have shown now is that V, and I'm going to explain this a little bit right now, that these sheaves have factorization presentations. They don't, so I'll explain what that means. They're not such a nice splitting principle, but it's something you can see that the sheaves are co-kernels of a resolution, functor applied to a resolution, as I'll describe. And as a consequence, we can show that in case A of B is finite, that these are actually coherent on MGN. So we don't need factorization for this. So this is, this is DUK that you get from the whole modular space. Okay, so that's the overview. The question now, so I'm going to write down what that here says. Oops, excuse me. And so I'm going to tell you what is a factorization resolution, and then I'll tell you the problem we're really interested in is whether you still have vector bundles in case you drop this condition of rationality. So I'm looking now at the least restrictive condition of finiteness, which is that A of B is finitely generated, and in this case, it could be not finite, it could be not semi-simple, but in case, so this is here. In case, then we don't know actually. We know that this is a state, if and only if statement. So we have such a bimodule decomposition of an algebra and as a finite sum of left and right A modules, if and only if the algebra is finite and semi-simple. So if it's C1 cofinite, it doesn't necessarily have to have sort of kind of factorization decomposition like that, but it has a resolution by such factorizable bimodules. So the first thing we show is that A of the has a resolution by and given any such resolution, this would look like you have a sum of left modules and right modules. I'm going to call them X0 and Y0. So these are left big module and right. And it keeps going. This is the resolution. So given any such resolution, then you can apply the bimodule functor. So you can apply this process of applying the bimodule functor, tensoring with the modules, and taking coinvariants, and as a composition of operations that's right exact. And this gives a presentation. So given any such resolution, we get a presentation where you're looking at the fibers of the sheaf at a pointed curve in the node, and you can do this as actually you apply this functor to A, and now you're on the normalization, and this looks like coherent of this resolution. So, we're summing over that X and Y, C tilde P by not the image of the functor applied to it. Okay, so this is true just in case B is C1 cofinite, and then in case the stronger finiteness assumption, there's a nice resolution that allows you to do this in a finite way, such that all the modules present are indeed composable. So the third part is if B is C2 cofinite, then you can achieve in 2. There's a resolution so that the presentation in 2 is finite, and the modules X and Y are indeed. And then the corollary to this is that if A of B is finite, then the sheaf is coherent. I mentioned that. All the fibers are finite on the whole of them. Okay, so those are the observations we've made, and now I will tell you a little bit more about the objects involved and some definitions. Are there any questions so far?
When you say resolution, do you have to bound on the length of the resolution?
That's a great question. So the resolution that we have is just given by the standard resolution of A, but in practice, all the examples we've worked on, we found finite resolutions, and we believe you can find a finite resolution. You may have to impose an additional condition on the algebra. But so far, we haven't found an example where you can't. And really, we're trying to show that you always have a finite solution.
That means the new developer, you have common before.
You have, sorry?
Common before.
Yeah,
Yeah.
right.
Yeah,
So,
yeah.
right. Right. I mean, we can always do that. Yeah.
Is this at least quasi-coherent?
It's quasi-coherent.
Quasi-coherent.
Yeah. Actually, all you need for a quasi-coherent sheaf is that the vertex algebra is CFT-type. And in that case, the modules have to be simple, but it's easy to reduce to the case that the modules are simple because everything is represented. And I mean, if you have any finiteness. So you actually have, there's a connection on the interior, a projectively flat connection if he is CFT-type, and it has singularities on the boundary. All right, so I want to say a little bit more about what are these vertex algebras and what are examples. The vertex algebras are some kind of generalizations of Lie algebras and associative algebras. They arise in a lot of contexts, not just in algebraic geometry, obviously. Every context, group theory, number theory, combinatorics. These are essentially conformal field theoretic being attached to a curve. Many more people study vertex algebras than study the modular space of curves. That's what I found when I look around the literature. So I said that the vertex algebra is a four-tuple consisting of a vector space. This is of CFT-type. With these two special elements, and I didn't address the last condition. So the last elements for vertex operator algebra are vertex operators. These are linear maps from D to ND valued power series. So they take now in A, the vertex algebra to a series, and the Fourier coefficients are in the vertex of the vertex. And this four-tuple has to satisfy a long list of conditions. Too much for the 20 minutes remaining in my talk. But I want to give you some idea of some of the properties. So for example, these are Laurent series. So if you take any two elements of the vertex algebra and evaluate the operator at the second. So take the operator to A, evaluate the B, certain endomorphisms, so this makes sense. Coefficients are endomorphisms. So you're just getting another element here in the vertex algebra. This funny indexing is the standard. What you know is that AM of B is 0 if M is large enough. So these are really Laurent series. So you can think about these as being in B transfer C under. And I should say that right now I'm working over C, but Borchard's original definition of vertex algebra was characteristic free. And a little bit has been done in characteristic P, for example, on these definitions. But there's definitely an opening for someone to define these sheaves in finite characteristic, and that would be interesting on the moduli space of curves because we've learned recently, for example, that in characteristic P, there are more external rays of the effective cone than say over C, and it would be interesting to see if you could produce such classes by taking Chern classes of these sheaves. Okay. So other conditions, this one I mentioned is in degree 0. And if you were to evaluate, if you take the associated vertex, this is like the identity. So these endomorphisms are either the identity of B if M is -1 or less than 0. zero. And similarly, if you do something interesting, if you plug in the degree 2 element omega, omega is the conformal vector. So for example, well, it's more standard and it's easier for me to think about this if I write Lm as omega m. This is convention. These operators, these endomorphisms, if you take them all together, and then if you take one more element and take their span, this gives a Virasoro algebra, a Virasoro Lie algebra. So these operators are subject to the Virasoro relations. I don't have space to write it there. Let me lift the board up. So the Virasoro relations. So first of all, this new element is in the center. I'm defining a bracket, and Lm is m minus n Lm plus n plus, well, you get something if n is equal to minus n. And what do you get? You get a quotient, this is defining, times this element k. So this, if I say what the k does to me, then I get an action of the Virasoro Lie algebra on the vertex algebra, which is very useful always to have anything acting on the object you're studying is very useful. And so we know how these elements act, and we say that k it acts by scalar. So we're going to scale with a number which we can choose. So we get a bunch of these vertex. This is the central charge, and we let this act by c times the identity. And so this has an impact on the Chern classes of the sheaves. When you compute the Chern classes of the sheaves, in case you get you're in a situation where you can compute the Chern classes if the vertex algebra is rational and C2 cofinite and self-dual and simple, then in the formula, these are tautological. So there are linear combinations of lambda classes, psi classes, and boundary classes. And the coefficients all depend on the rank of the bundle, and then this central charge, and also similar invariance of the moduli. So conformal of the modules. Okay, so this is super important. It's essentially up to Q, the coefficient of lambda in the classes. Okay, so what does it mean for the vertex algebra to be finite in the most loose way? This is strongly finitely generated. And then if it's strongly finitely generated degree 1, the classes are fully generated. So it's strongly finitely generated if there are elements A1 through AR in V such that the vector space is the span of strings of these. And the strings look like AI1 to the minus N1. So these AI2, N2, these are the endomorphisms acting on this backing. So here the NIs are Z, and they're non-negative. And you can compute the degree of such an element. Like the degree of A minus M is the degree of A plus M minus 1. And so if actually these NIs are always bigger than or equal to 1, and so these are always non-negative. And R 0. So this is really how you work with the vertex algebras. They look almost like universal enveloping algebras of Lie algebras. That's the feel of the elements. And you can construct VOAs using a lot of different techniques. One sort of basic technique is to start with a Lie algebra, such as the Virasoro Lie algebra, or a simple Lie algebra, and then you produce the vertex algebra as a model using the universal enveloping algebra of the Lie algebra. So it looks a lot like, when you do this for a simple Lie algebra, it looks like an affine Lie algebra. That's really what it has the feel of. And so let me check the time. So would you like to see an example, or should I just tell you about modules? Maybe.
The example.
Yeah, I mean, it's really hard. I think that's why I wanted to say the results in the beginning, because it's really technical. Okay, so one simple vertex algebra comes from the Virasoro algebra. This is really the simplest one. Algebra, if you remember, I here, C is the span of these L and V extra element, okay, which is going to become the vacuum vector. So the way that we do this is a Lie algebra, and it has a decomposition, a trigonal decomposition. So there's C into negative part, degree 0 part, and a positive part. And the negative part, for example, so here, C negative is just this the span of these operators, where you take L minus n, and you go from n equals 1 to infinity, and the positive part is just the other ones from 1 to infinity, and the middle part, the degree 0 part, is the span of this L0 operator. I didn't say what L0 does, it's a grading operator, actually. If you apply it to an element, it'll tell you it's a grade. So the idea is to take that K and make it into a trivial module. And I'll call this VC is the vertex algebra. It's really the free algebra over the universal enveloping algebra of this VRC negative. But how do you construct it? You know how the degree 0 part acts on 1, it's just in degree 0, so it's acting by 0, and then you can make you can say that the positive part also acts in degree 0. So we're going to let 1b be the induced module, thinking of 1b as a module over the non-negative part, where it's just acting trivially, and then inducing it up to the whole thing. Okay, so this is actually not quite what we want. It's a little bit complicated. It has a maximal submodule. There's a singular vector and some other things that we want to mod out by. And when we take, so for example, the element singular vector is L minus 1 times 1b. And when we mod out by this maximal submodule, we get a nice simple vertex algebra. And what we know, for example, about the geometry of this vertex algebra so that when you take this quotient, the Giroux algebra is So C, if C is not equal to a particular nice rational number, 1 minus 6 times q squared over p times q. If it's not that, then the Q algebra is just finitely generated, C adjoint X. So it's still in our nice category of C1 finite. But if the central charge is equal to CQQ, then it's a quotient by an ideal generated by a polynomial. And so we know everything about the polynomial. We know its expression is the degree is p minus 1 times q minus 1 over 2, and p and q are relatively prime. So this is a concrete example. You can do this process of making what's called a vacuum module with lots of different things. You can produce a Virasoro algebra from a simple algebra to the affine, universal affine VOA, or a simple quotient, simple affine VOA. You can use lattices to produce vertex algebras. You can then produce more vertex algebras by taking orbifold or quotient constructions, entering them together, and just doing a lot of different things. And in this case, for example, these are rational n-tuples finite. These are not generated in degree 1, as the vector space it's spanned by elements that look like L minus M1 dot dot dot. L minus MR times 1, where the M1 MR. So you can arrange using a commutator formula for these to be decreasing, and there are these 2. So this actually, so you have the degree 0 element, and then you have nothing in degree 1. This is generated in degree 2. So the generators are 1 and omega. Affine VOAs are all generated in degree 1. So they're all globally generated from VO0. And there are more general vertex algebras that are really of interest, called the triplets, which are not rational. They're called irrational. But they're C2 finite. And this all applies. Okay, so the last thing I'm going to tell you just briefly is how I don't have much time left. So I haven't defined a V module, but if you ask, you could ask me what a V module is after the talk or later in the conference, and I can tell you and show you how to prove coherence and everything else. So I think this is a good stop.
Are there more questions?
So if we're talking about MGN or MGN5,
yeah.
then lots of people now have worked on tautological price.
Yeah.
And it's also known that there is infinitely more to that.
Right, so there are conjectures about the structure of the tautological ring. Is that what you're talking about? Due to Chern?
Yes, but what's left?
What's left is, so, yeah.
You're making serious inroads.
Well, potentially, because this is a new source of elements in the tautological ring. And right now, well, of course, the generators are known, and there are conjecture relations for the tautological ring by Aaron Pixton. And I mean, these are examples that one could test his conjectures on. I mean, they're new classes in the tautological ring, and so it doesn't. We don't know if they're subject to the relations that Aaron has. I think that's a really it should be checked. Yes. So the sheaves emit a projectively flat connection on the interior, on MGN, the moduli space of smooth pointed curves of genus G. The connection, it extends to the boundary. It extends, but it has singularities on the boundary. Yes, and right, and there's something that I just didn't mention. I didn't tell you the definition of the modules, but they all depend on coordinatized curves. So in fact, all of the structure is defined on a moduli space of pointed coordinatized curves. Everything is proved on a bigger moduli space, much bigger than MGN bar. And then one has to descend to MGN bar. And showing the descent itself is complicated. And the only really simple proof of the descent exists for this class of C1 cofinite. So you can define the sheaves on this MGN, this cover moduli space of pointed coordinatized curves. The connection exists with very little, assumption. But to descend everything to MGN is complicated, and it works more easily in this context. Thank you for the questions. Yes, great. Great. Yes. Yes. Yeah, theta functions. Right, so let me comment on that. So I should have said earlier that, this whole story started in the 90s. The first two examples were affine VOAs studied by Suchier, and Virasoro VOAs studied by Bailenson and Drinfeld. And they proved everything that I've said for those two examples. And then some other work was done in low genus for more restrictive situations. What's neat about affine VOAs are like the gift that keeps on giving. I mean, if you look at the fibers and you take their dual vector spaces, those are called vector spaces of conformal blocks, and they're isomorphic, canonically isomorphic to generalized theta functions. And actually with the Virasoro, you get theta functions. And so it's a natural question to ask if you have, when you look at the vector bundles of conformal blocks, which are the dual bundles, if you look at their fibers, is there a geometric interpretation in terms of, like global sections of a canonical line bundle on bun G for some G? And the guess that we have is that the first degree, so this vertex algebra is a sum of vector spaces, and V1 is always a Lie algebra, always. The axioms of the VOA give that it has the structure of a Lie algebra. Okay, so maybe if you take a group that has that as its Lie algebra, of course there are a number of groups that have that as its Lie algebra, but if you take one with, there's one you can look at that's more likely to be it, then what about looking at a line bundle on bun G for that G? And I mean, that works in the two cases, because in the Virasoro case, there's no degree zero, and that's why you get theta functions. And for the affine VOA, you get, we know how to prove that in case the vertex algebra is generated degree 1 and self-dual and simple. And the reason for that is, in that case, it's a tensor product of the affine VOAs for different levels and different groups. And you can modify the structure, get the theta functions, kind of formally. It's not very interesting. But on the other hand, because you can show that every module over any VOA is a module over that Lie algebra, that degree 1 component Lie algebra, it's possible that you could extend that information forward in cases where you actually have a V1 that's not trivial. So I think that there's definitely a chance for that. And that is one of the problems that I'm very interested in working on. Yeah, thank you.